Hello, everyone. In our class last Thursday, we talked about the measure of central tendency, mean, median, and mode. And today I will continue and pick up from there. So in these three pictures, you will see a little bit more of this in next chapters. It's about if your distribution of the data is symmetric, if it's left skewed or if it's right skewed, how the position of each of the central tendency method measures would be. For example, when it's symmetric, which means 50% of the data are less than mean and or median and 50% are more, mean, median, and mode are in the same place. For the left skewed, mode is like the biggest number and mean is the lowest and median is in the between because you have more extreme values on the left side. And then for the right skewed distribution, you will see the mean in like bigger because again, more extreme values are on the right side, and mode would be the smallest one. After this one, we will talk about like a summary of mode, median, and mean. If you remember, I said the only central tendency that you can have if you have only the nominal measure, which means there is no order like the colors that I always refer to, then mode would be the only one that you can actually consider as a measure of central tendency. You cannot calculate median because there is no order, and mean because it's not in numeric format. The same thing for the mean if it's ordinal, but if it's not number, so distance is not meaningful. So you cannot have the average of the numbers of the objects if they are not in numeric format, but you can have median because you can rank them. So the median is, you can measure it, and also for mode. And for the interval and ratio, because if you remember from chapter 1, both of them are numbers. So both median, mean are, you can calculate them, as well as mode because you could do it for all of the measures. So mode is the only measure of tendency or that you can calculate for all of the 4 measurements, scale of measurements. But for mean, only when it's numeric, which is, it has to be interval or ratio. The next one is about the weighted mean. We will connect this concept to the probability in module 2. You will see a little bit more of it. And then the concept is about your data has some weight. Sometimes it can be like how many of the specific value you have in the data, that would be the weight of it. And then to calculate the weighted mean, you will multiply the weight of each of the observation or values by the value, and then add them together, divide by the summation of all of the weight. That would be the x bar sub w. We show it with this, which is x bar of sub w, x1 to xn. They are the set of numbers or values that you have in your data set, and w1 to wn, they are the corresponding weights. So here is an example. You can look at it. It's about the pays. Either they are like for the employees, either they make $16.50 per hours, 19 per hours, or 25 per hours. And then in general, they have 26 of this type of employee that they pay them hourly. And 16 of them are paid at the rate of 16.50, 10 at the rate of 19, and 2 at the rate of 25. So now if you want to see what's the average of this 26 hourly employee pay, you need to use a weighted mean. So 14 of them, they make 16.50, 10 of them $19, and 2 of them 25. This one has to be 25. I need to fix it. And then divide by the number of employees, 14, 10, and 2. So $18.11 is the weighted mean for this employee. So in average, this 26 employees, they make $18.11. So now we are done with the measure of central tendency, which again was mean, median, and mode, and also weighted mean. And now we want to talk about the dispersion and why we study that. When we are talking about the measure of location, we are talking about only the center where they are concentrated, right? But we don't have anything about how is the spread or variation of the values. So because of that, we need to have a measure to see what's the dispersion or the variation of the data around the mean. So to do that, we will have three different ones in this chapter: range, variance, and standard deviation. You already know the range because we used it when we wanted to see what's the interval for our histogram. So for the range is the like one of them that is it very easy to calculate, maximum minus minimum. Here we have two different data sets. Both of them, the measure of central tendency is the same, but as you can see, they are like the spread of them around the mean is a lot different. So this one is a lot more concentrated around the mean, but in this one, you have a lot more spread. So if we want to calculate the range, which is maximum value minus minimum value, we can compare these to the dispersion or spread of these two data sets with each other. And if you remember, the mean was influenced by the extreme values in this range, like in the measure of dispersion. Range is influenced by extreme values as well. So for the first one, we have minimum and maximum. Minimum 48, maximum 52. If we subtract 4 is the range. And then for the second location, we have the maximum of 60 and minimum of 40, 20. So as you can see, the range of the second one is almost 5 times like for the second location than the first one. So we see the mean, which is average 50 for both of them. Measure of central tendency, but dispersion is a lot different between these two. So if we consider these two together, it will give us a lot more information than only central tendency by itself. The second one is population variance. So that is like the drawback or the like a weak point for the range was it's only about two numbers, maximum and minimum. But we want to know a little bit more information. If we want to know a little bit more information, variance and standard deviation later would be a better candidate. So usually I recommend to look at all of them together if you want to have a little bit more information about your data. So variance actually is about how much the values are vary from their mean. So because it's the variation of the values like compared to their mean, in the formula, you can see we have a sigma squared here, which is for the population variance. And then is x, which is each of your values minus the average or the mean of these values. And the reason we use the square, if you recall from the beginning of the chapter, the difference between each of the values and their mean would be 0. So if we add all of them together without square, it will be 0. So two like actually cancel that and make that effect to not be in effect. Otherwise it will be 0, right? The sigma x minus mu would be 0. So we use square. So that gives us the opportunity to actually see the differences, absolute value of the differences. So x minus mu squared divided by n, which is the population size. And again, for the population, we use n. So that gives us the standard, the population variation or variance. And then we can just, here is just the steps how to do. So the first step would be we need to know what's the mean of the population. And then the second step would be calculate the difference between each of the values and their mean, and then square all of them, add all of them together, and finally divide by n, which is the population size. So here is an example. it's about the number of traffic citations by month and January to February to see what's the variance of this. First step would be to calculate each of these 19. The first step is to calculate the average, which is just add all of them together, divide by 12, which is the number of observation, 29. The second step would be to calculate the difference between each of the values. For example, 19 by 29, which is negative 10. The second one, 17, the difference of 17 and 29 minus 12, and all the way to the last one, which is December, the difference between 10 and 29, negative 19. And then square all of them. So a square of negative 100, negative 12, 144, all the way to the last one, which is 361. And then add all of this together, the square of the differences, and then divide them by the 12, which is the n. So one of the things that you need to consider is the unit of the variance is the square of the observations. So whatever is all of this like units of the citation, for this it would be squared. So to basically have a little bit more, like make it a little bit easier to understand and interpret, we use the standard deviation, which is the only difference is the square root of variance. So the good thing about that is now the unit of the standard deviation would be exactly the same as your observation. So for variance, what 124 citations square, but for standard deviation, it will be citation. So you would have a same unit for the dispersion ratio, which is in this case the standard deviation, and for your observation. So that's the good thing about standard deviation, makes the interpretation a lot easier. So all it is just adding a square root of that variance. So now you learn about the population standard deviation and also variance. For the sample, the only difference would be the notation first. For the mean, instead of mu, we have x bar, but how you calculate it, again, summation of all of the values divided by the sample size. But the main difference would be for variance, we have divide by n, so the difference of each of the values and their mean squared, summation divide by n, which is the population size. But for the standard deviation and variance of the sample, we use n minus 1. So this part is very important. Again, the definition is the same, the difference between each of the values and their average squared, and then summation divide by, and instead of n, here we have n minus 1. And the same thing for standard deviation, square root of this, and we have n minus 1 in the denominator. And again, the measure for this one, variance of the sample would be whatever is the unit of the values squared. But for standard deviation, it will be same as the values that we have. Here is the example. So we have only some of the employees' information. So first, you need to calculate the average of sample, which is just add all of these values together, divide by 5. And then second step, calculate the difference between each of the values and their mean, and then square each of them, add them together, and then divide by n minus 1, which is 5 minus 1. So it's $10 squared is the variance of the sample, and then if you calculate the square root, it will be $3.16. So as you can see, the unit of the standard deviation is the same as each of your observation, which is dollars in this case. So in general, if you want to like interpret and see what are the uses of standard deviation, it's actually used to compare the spread of two or more set of observations. So if we have different observations and a set of observation, and we want to compare which one is like a spread more, like is like more spread out in compared to mean, or one of them is more concentrated, we will use that. If it's a small, it means the values are closer to the mean, the same as the example we saw for two locations. And if it's large, it means the values are widely scattered about the mean. There is a Chebyshev theorem, which is about the dispersion of the data around the mean. And this is about any sets of the observation. If we don't know if they are symmetric or they are left skewed or right skewed or any other type of distribution, always we can say the proportion of the values within k standard deviation from the mean is at least 1 minus 1 over k squared for k greater than 1. So if we have like k equal 2, if we plug them in the equation, it will be 0.75, meaning at least 75% of the observation are within 2 standard deviation from mean. So this k equal 2 basically is how many standard deviation the observation are from the mean. And if it's k equal to 3, it means almost it's 0.889, or we can say at least 88.9% of the observation are within 3 standard deviation from the mean. So look at this like picture. So here are like different colors that I put. The mean is this one, which is almost 50. And then here is the data that they are within 2 standard deviation, this a little bit darker shade. So it means at least 75% of the data are between 2 standard deviation below the mean and 2 standard deviation above the mean. And then if k equal to 3 is almost 89%. So we say at least 89% of the data you see is a little bit lighter shade than the 2 standard deviation. So they are within 3 standard deviation below and 3 standard deviation above the mean. And lastly, for the 4 is at least 94%, but we see it's like only maybe two observations are here below 3 standard deviation. So almost is 100%, but we say at least 94%, right? So 100% is in that range. So that's how like the Chebyshev theorem is about. And then here there are some like example. It says they have the average of $51.54 of contribution, and then which is this profit sharing plan is every 2 weeks, and the standard deviation is 7.51. So in asking at least what proportion of employees make a contribution within 3.5 standard deviation of the mean. So it means 3.5 standard deviation below the mean and 3.5 standard deviation above the mean. So if we want to calculate those two values, it would be the average minus 3.5 times standard deviation. That gives us the lower limit for 3.5 standard deviation below the mean, and the second one plus average plus 3.5 standard deviation will give us the upper bound of the 3.5 standard deviation, which is above the mean. So if we put 3.5 in the Chebyshev theorem formula, we will have 92, meaning at least 92% of the employees in this company will contribute between $25.26 and $77.83, which is within 3-point standard deviation within the mean. So if our Chebyshev theorem is something very general, it's for any sets of the values regardless of the shape of the distribution. But if we have the information about the shape, which is symmetrical and bell-shaped, we define it. We will see a lot more of this in chapter 7. And then we can just be more precise. And instead of at least, we can say if we have, we call it empirical rule or normal rule theorem, which is about one standard deviation of the mean is about 68% of the values. Two standard deviation of the mean, again, below and above the mean, will have 95% of the values, and 99% will have with the values within 3 standard deviation of the mean. And here is an example. We have a mean of 100 and a standard deviation of 10. And then if you calculate one standard deviation below the mean, which is 100 minus 90 and 100 plus 10 for above the mean, so between 90 and 110 will be within one standard deviation of mean, which is 68% of the data, within two standard deviation from the mean, which is 100 minus 2 times 10 and 100 plus 2 times 10, which is 80 and 120 will be 95%. And then finally for the 3 standard deviation, which is 100 minus 3 times 10 and 100 plus 3 times 10, between 70 and 130, it will be 99.7% of the data. We will talk about a lot of this in chapter 7 again when we talk about normal distribution, but right now it's just about the empirical rule theorem. And here is just an example with different mean and standard deviation. And here is just a thing about this chapter that we left off last Thursday. When we come back on campus, I will start with the chapter 3 practice problem to just have some review, and then we will start chapter 4. I hope all of you are staying warm, and see you next time. Bye.